This has been Elliott's ENME351 Lab 1. So starting with the pre-lab, problem 1, here's the truth table with the intermediate steps included for the A and S naught and B and S terms. Fill that there. Now when it comes to creating AND gates out of transistors, here's my circuit that I came up with using 2 transistors in series and then a third one, which effectively acts as a NOT gate, because when these 2 terms are 0, this term will be 5 volts because it's not connected to ground. But when both of these are activated, it will be connected to ground and be 0, so we'll need the NOT. And as you can see, it only outputs 5 volts here when both these terms are at 5 volts, and not when only one of them is. So it's working correctly. For the OR gate, I did a very similar thing, except the first 2 resistors for VA and VB, transistors, sorry, are in parallel, not in series. And again, now when either A or B, or both A and B, are high, the output will also be high. So that's good. The NOT gate, straightforward from the example. And when A is 0, Z is 5, and when A is 5, Z is effectively 0. Going on to number 3, creating the logic diagram from the expression for Z. Here's the logic diagram I came up with. Working backwards, we have the OR from the 2 ANDs, and one of the ANDs is from the NOT, representing those 2 ANDs and that OR. And the truth table matches, so when S is equal to 0, it only outputs at high when A is at high, like there and in that term. And then when S is high, it only outputs as high when B is high, so that term, that term. For number 4, we made the logic expression into a physical breadboard integrated circuit expression using the NOT and OR chips. And so you can see the truth table is the same, where when S is low, the A term decides whether or not Z outputs. And then when the S term is high, the B term decides whether or not it outputs. You can see the LED is lit up when the B term is high, not lit up when the B term is low. Then for number 5, turning this expression for the 4-to-1 multiplexer into creating that from 3 2-to-1s. You have the inputs A, B, C, and D into the 2 2-to-1s with the selector 0, and then selector 1 here, output Z there. Moving on to the lab, we created the same circuit you saw above from Tinkercad in the physical one, so where you picked the wires and moved them to get different results. You can see that here the truth table matches that one perfectly. So when S is 0, the A term determines whether or not the LED is on, and when S is 5 or high, the B term determines whether or not the LED is on. And then here is the problem 3, where it is blinking at a rate of 2 Hertz because the S term, the green wire, is plugged high, so the B term, or pin 8, is determining what rate it blinks at, which is 2 Hertz. But then when you switch the pin to high, it starts blinking at a rate of 10 Hertz. And here is my code for that on the computer, where I just have a bunch of delays turning pin 4 on and then off. And then after 1 second, I turn pin 8 off, and then after another second, I turn it on, resulting in pin 8 turning on and off at a rate of once every 2 seconds, and pin 4 turning off at a rate of 4 times every second. Thank you.